snake the length of a school bus once coiled through Colombian swamps, crushing crocodiles with the same ease you'd crumple paper. Then it vanished. Not from hunting, not from disease, but from something far stranger. The story begins in 2009 when paleontologists in a Colombian coal mine unearthed vertebrae thicker than human wrists and immediately assumed they'd found ancient crocodiles. They were wrong. The Cerrejón coal mine isn't just a fossil site. It's a snapshot of Earth 60 million years ago, preserved under layers of compressed rock and ancient vegetation. When researchers first examined these massive bones, every measurement pointed to crocodilians. Giant reptiles dominated those swamps, and finding enormous vertebrae seemed routine. But the curves were wrong. The shape didn't match. Someone ran the numbers again, checked the anatomy twice, and realized they were holding snake bones. Not just any snake bones. These belonged to an animal that rewrote the biological rulebook. Titanoboa measured somewhere between 42 and 50 feet long. Weight estimates hover around 2,500 pounds. For context, the biggest anaconda ever reliably documented stretched 28 feet and weighed 500 pounds. This prehistoric serpent was nearly double the length and 5 times heavier. When scientists announced these numbers, the paleontology community went silent. Nothing alive today comes close to this scale. How do you even calculate the size of an extinct animal from scattered vertebrae? Modern snakes follow predictable patterns. Their vertebrae scale proportionally with body length. Measure a vertebra from a living boa constrictor, note its body length, and you've got a ratio. Apply that ratio to fossil vertebrae, and the math reveals total size. But Titanoboa's vertebrae were so massive that researchers triple-checked their calculations, convinced they'd made an error. They hadn't. The numbers held. But here's what makes this discovery truly bizarre. Size alone doesn't explain why Titanoboa existed. The real answer sits in the physics of being cold-blooded. Snakes are ectotherms. Their bodies can't generate heat internally. They absorb warmth from their surroundings, which means environmental temperature directly controls their metabolism. Warmer climates accelerate digestion, speed up growth, and permit larger body mass. So when paleontologists pulled those vertebrae from Colombian rock, they weren't just discovering a giant predator. They were reading a climate record written in bone. The Earth 60 million years ago barely resembles our planet. The Paleocene epoch followed the dinosaur extinction, and the world was rebuilding from scratch. But it was rebuilding hot. Northern Colombia sat at average year-round temperatures around 90 degrees Fahrenheit, with almost no seasonal variation. Imagine a rainforest that never experiences winter, never cools at night, never offers relief from humid, stifling heat. No ice caps existed anywhere. The poles were temperate. The tropics were furnaces. Modern rainforests, the Amazon, the Congo, Southeast Asian jungles, are actually too cool for a snake like Titanoboa to survive. Today's largest constrictors push against the thermal limits our current climate allows. Growing beyond anaconda size requires sustained heat, not for months, but for millions of years. Titanoboa's metabolism demanded that constant warmth to pump blood through 50 feet of muscle and process the enormous prey it consumed. The Cerrejón site reveals this ancient world in extraordinary detail. Layer after layer contains fossilized plants that existed nowhere outside tropical zones. Giant turtle shells the size of dining tables. Early crocodile relatives with blunt, crushing jaws designed for cracking hard-shelled prey. These weren't sleek, fast-moving river hunters. They were heavy-bodied ambush predators built like tanks. The environment itself tells a story. This wasn't clear, flowing water. Cerrejón was a humid swamp system with murky, slow-moving channels choked by tangled roots and dense vegetation. Visibility would have been terrible. Sound muffled by constant rainfall and buzzing insects. In that environment, size became an overwhelming advantage. A snake longer than a city bus could lurk completely submerged, its body hidden in tannin-stained water, supported entirely by buoyancy. Heat and humidity kept its muscles warm and ready. It didn't need to chase prey. It simply waited, sometimes for days, until something came within striking range. Then it moved. Biomechanical models estimate Titanoboa could generate over 400 pounds per square inch of constriction pressure. That's enough force to shatter ribs instantly. Modern pythons kill through blood flow restriction, slowly cutting off circulation until prey loses consciousness. At Titanoboa's size, that distinction becomes meaningless. Whatever it wrapped around simply stopped existing as a living thing. The fossil record from Serra tells us what it hunted. Giant turtles, slow-moving and calorie-dense, made ideal prey. Early crocodiles, smaller than Titanoboa, and not yet evolved into the apex predators they'd later become. Large fish common in the river systems, possibly early mammals, though mammals remained relatively small during the Paleocene. Anything that ventured too close to the water's edge risked becoming a meal. Water wasn't just Titanoboa's hunting ground. It was survival infrastructure. The buoyancy of water supported its massive weight. On land, 40+ feet of muscle doesn't glide smoothly. It drags. It fights gravity with every movement. Internal organs get compressed by body mass. Breathing becomes difficult. Digestion slows dramatically. Movement turns exhausting. But submerged, all those problems disappear. Water also helped regulate body temperature. Even in the sweltering Paleocene climate, a snake this large needed ways to avoid overheating. Submerging in slightly cooler water provided that relief, while maintaining the high metabolic rate necessary to sustain such size. So picture this accurately. Not a serpent slithering across land like some nightmare creature. Instead, see it gliding silently through dark water, eyes barely above the surface, body invisible beneath murky currents, waiting with the patience only an ambush predator truly understands. But something happened. Something that erased Titanoboa from existence entirely. Not predation, not disease, not competition from other species. The world itself changed. And when it did, every advantage Titanoboa possessed became a fatal weakness. What killed the largest snake that ever lived wasn't violent. It was quiet, gradual, and absolutely unavoidable. The answer lies in understanding what happens when a planet built for giants slowly becomes a planet that can't support them anymore. After the Paleocene epoch ended, Earth entered a cooling phase. Not suddenly, not catastrophically at first. Just gradually, almost imperceptibly, temperatures began dropping across the globe. Average annual temperatures fell by several degrees Celsius over the span of a few million years. For warm-blooded creatures, this represented an adjustment. For Titanoboa, it was an extinction event unfolding in geological slow motion. Here's what happens to an ectothermic giant when its world cools. Metabolism slows immediately. Every biological process that depends on heat, digestion, muscle function, neural activity begins operating at reduced efficiency. A snake that once processed a massive meal in 2 weeks now requires a month. Movement that felt fluid becomes labored. Hunting success rates plummet because reaction times decline. The animal needs the same amount of food to maintain body mass, but now it burns fewer calories and can't acquire prey as effectively. It's a mathematical death spiral with no escape route. Titanoboa couldn't simply migrate to warmer regions. The entire planet was cooling. Tropical zones that once maintained year-round sauna conditions now experience seasonal temperature variation. Swamps that never dropped below 30 degrees Celsius started seeing cooler periods. For a creature built exclusively for extreme heat, even modest cooling proved catastrophic. Its body wasn't designed with thermal margins. Evolution had optimized every system for one specific climate regime, and that regime was disappearing. But temperature alone doesn't explain the full collapse. The ecosystem supporting Titanoboa began fragmenting from multiple directions simultaneously. Mammals, which had remained relatively small and insignificant throughout the Paleocene, suddenly exploded in diversity and size. These warm-blooded competitors possessed one decisive advantage. They remained active regardless of ambient temperature. When morning temperatures dropped, mammals kept hunting. Titanoboa had to wait for the sun to warm its body. That delay cost opportunities. Prey became scarcer. Competition intensified. The swamp systems themselves were transforming. As global temperatures cooled, precipitation patterns shifted. The year-round deluge that maintained Cerrejon's waterlogged environment became more seasonal. Dry periods emerged. Rivers that once flowed constantly began experiencing low water seasons. Dense vegetation thinned in some areas. Titanoboa needed continuous water to support its weight and facilitate hunting. Fragmented waterways meant fragmented habitat. Populations became isolated. Genetic diversity declined. Then the prey base collapsed. Giant turtles, those slow-moving calorie packages that formed a dietary staple, were also ectothermic. They faced identical metabolic challenges. As temperatures dropped, turtle populations declined sharply. Early crocodiles, similarly cold-blooded, struggled with the same thermal constraints. Large fish populations fluctuated with changing water conditions. Everything Titanoboa hunted was simultaneously declining or adapting in ways that made them less available. The entire food web supporting apex reptilian predators was disintegrating layer by layer. Some scientists estimate the transition took roughly 3 to 5 million years. That sounds gradual, but evolution doesn't operate on human timescales. For a species with Titanoboa's specific requirements, that window wasn't long enough to adapt significantly. Body size in snakes correlates directly with environmental temperature through fundamental physical laws. You can't evolve around thermodynamics. A smaller Titanoboa might survive cooler conditions, but then it's no longer Titanoboa. It's something else competing against animals already better adapted to the new environment. There's no evidence of transitional forms, no medium-sized descendants struggling along in marginal habitats. The fossil record shows Titanoboa present in Paleocene deposits, then absent afterward. Clean disappearance. This suggests the species didn't gradually shrink or adapt. It simply failed to reproduce successfully as conditions deteriorated. Fewer eggs hatched. Hatchlings grew more slowly. Juvenile mortality increased. Within a few generations, the population dropped below viable levels, then it was gone. What replaced it? Smaller reptiles better suited to variable temperatures. Early mammals expanding into predatory niches. Eventually, crocodilians would return to dominance in tropical waterways. But by then, they'd evolved different body plans and thermal strategies. The age of giant ectothermic land predators had ended. Warm-blooded mammals would inherit that role across most ecosystems. Reptiles would persist, but never again at Titanoboa's scale. The lesson here cuts deeper than one extinct species. Titanoboa represents what happens when an organism becomes too specialized for one specific set of conditions. Its size was both supreme adaptation and fatal vulnerability. In the scorching Paleocene, nothing could challenge a 40-foot ambush predator with bone-crushing constriction force. But specialization creates fragility. When the environment shifts, specialists have nowhere to go. Generalists survive disruption. Specialists vanish. This pattern repeats throughout Earth's history. Extreme adaptations produce temporary dominance, followed by extinction when conditions change. The largest animals, the most specialized hunters, the creatures perfectly tuned to one specific world, they're always the first to disappear when that world transforms. Titanoboa mastered an environment that existed for roughly 10 million years. Then that environment ceased existing, and so did Titanoboa. We're watching similar dynamics unfold today, just compressed into timescales humans can witness directly. Modern ecosystems are shifting faster than most species can adapt. The difference is we're the cause this time, not gradual geological processes. Climate zones are moving, precipitation patterns are changing, temperature ranges are shifting. Species adapted to narrow conditions are already disappearing. The mechanisms are identical to what killed Titanoboa, just faster. Cerashon's fossils preserve a moment when Earth supported life at extremes we can barely imagine. Forests so hot and wet that 40-foot snakes thrived in swamps stretching across continents. That world ended not through catastrophe, but through incremental change, accumulating until the system couldn't support its largest inhabitants anymore. The bones remaining tell us what was and what can never be again. Titanoboa existed because conditions aligned perfectly for exactly long enough. Then those conditions shifted by just a few degrees, and the largest snake that ever lived became impossible. Not unlikely, not rare, impossible. The planet simply stopped producing environments that could sustain it. That's how most extinctions actually work. Not dramatic impacts or sudden die-offs, but slow elimination of the specific conditions required for existence. The world moves on. The specialists don't. Every fossil tells two stories: what lived and what made living possible. Titanoboa's bones reveal both. They show us an animal that shouldn't exist by our current understanding of biological limits, and they show us why it can't exist now. The Paleocene world was fundamentally different from ours, not just in temperature, but in the rules governing what forms life could take. When those rules changed, Titanoboa had no appeals process. It simply stopped being viable. We tend to think of extinction as failure, but that misses the point entirely. Titanoboa didn't fail. It succeeded perfectly for millions of years in the only environment where success was possible. The real question isn't why it went extinct. It's why we're surprised when hyper-specialized organisms can't survive environmental shifts they never evolved to handle. The planet doesn't owe any species stability. It just keeps changing, and life either adapts or it doesn't. What makes Titanoboa genuinely unsettling isn't its size or its hunting methods. It's how completely it vanished when conditions shifted by margins that seemed trivial on paper. A few degrees cooler, slightly less rainfall, more seasonal variation. That's all it took to erase the largest predatory snake in Earth's history. No dramatic impact event, no volcanic catastrophe, just the planet cooling slightly and an entire branch of evolutionary possibility closing forever. That should probably concern us more than it does. We're currently pushing global systems through changes that make the Paleocene-Eocene transition look gentle by comparison. We're doing it faster, more chaotically, and we're watching species disappear in real time. The mechanisms haven't changed. Organisms adapted to specific conditions lose those conditions and can't adapt quickly enough to survive what comes next. We know how this story ends because we've read it in stone millions of times. The specialized giants always go first.